everyone, I hope you're all doing well. Last time we were discussing how to calculate the number of atoms in a sample of a pure element. We also talked about the concept of the mole, and in order to go from moles to atoms, we used a number called Avogadro's number. Today, we're going to apply that same concept to molecules. So let's calculate the number of molecules in 0.362 moles of water. So as usual, let's start by writing out what we're given, and then what we need, and then what our plan is. So we're told that we have 0.362 moles of water, which is H2O. And then we need to determine how many molecules of H2O we have. So our plan is to go from moles to molecules. Now, in our previous lecture, we saw that Avogadro's number can be used to go between moles and something that you're counting. So in this case, we're counting molecules. So that means that 1 mole of H2O is equal to 6.022 times 10 to the 23rd molecules of water. So now we can use this equality as a conversion factor. So we're going to start with what we were given, which was the number of moles of H2O. And then we're going to set up our conversion factor. And remember that we always want our desired unit in the numerator, and then we'll put the other unit in the denominator in order to cancel it with our given unit. So in this case, we want to end up with molecules of H2O, so that means we're going to put Avogadro's number in the numerator. It's a very large number, so I need to expand my conversion line there. Now in the denominator, we're going to put 1 mole of H2O so that it cancels with our given unit. So let's show the units canceling. And if we simplify this, we end up with 0.362 times 6.022 times 10 to the 23rd, and our final unit will be molecules of H2O. So now if we plug that into our calculator, we should end up with a value of 2.18 times 10 to the 23rd molecules of H2O. Now, just make sure that you're getting the same answer in your calculator, because sometimes it can be a little tricky to plug in powers of 10. Now, one other thing to take note of is if you're calculating the number of molecules, that should be a fairly large number. So in this example, we had something on the order of 10 to the 23rd. However, if you're calculating the number of moles, that should be somewhat small. So that is on the order of 10 to the negative 1. So if you're doing a calculation, and let's say you end up with a really large number of moles, you might want to go back and double check that you set your problem up correctly. Same goes if you calculate a really small number of molecules. You might want to go back and double check that your work is correct. Okay, So we just applied the mole concept to molecules, but we can also apply this concept to the individual atoms that are contained in the molecules. So an example for this, using the compound carbon dioxide, if we have 1 mole of carbon dioxide molecules, that means that we have 1 mole of carbon atoms and 2 moles of oxygen atoms. So you'll notice in the formula for carbon dioxide, we have 1 carbon and 2 oxygens. So we can use that 2-to-1 ratio in order to determine the ratio between carbon dioxide and each type of atom. Now, this also means that if we have 6.02 times 10 to the 23rd molecules of carbon dioxide, then we also have Avogadro's number of carbon atoms, and we have twice that number of oxygen atoms. And this just has to do with that ratio again, the 2-to-1 ratio. And the same goes for mass. We can set an equality here, and the molar mass of carbon dioxide is 44.01 grams. And that's equal to the mass of carbon plus 2 times the mass of oxygen. And if we look on a periodic table, the mass of carbon is 12.01 and the mass of oxygen is 16, but we have 2 oxygens, so we actually have a mass of 32 grams of oxygen. And those both add up to 44.01 grams for carbon dioxide. Now, what's great is we can use all of these different equalities in solving numerical problems. So let's write out a few of the possible factors for carbon dioxide that we could use in a problem. So to start, we could write some conversion factors involving the ratio of carbon to carbon dioxide. So if we have 1 mole of carbon dioxide, we also have 1 mole of carbon. If we have 1 mole of carbon dioxide, that means we have 2 moles of oxygen. Now, we could also flip these two ratios in order to solve for, let's say, just moles of carbon or just moles of oxygen. Remember that you just need to take into account your given unit and your desired unit, and the desired unit should always be in the numerator. So we can flip the factors depending on the desired unit, which should always be in the numerator. Now, some other factors that we could use are the molar masses. So we saw that there are 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. There's also 12.01 grams of carbon for every 1 mole of carbon. And then 16 grams of oxygen for every 1 mole of oxygen. So again, these are all molar masses, and we can use these to convert between grams and moles. And then finally, we have Avogadro's number. Let's see, I'll use green this time. So if we have 6.022 times 10 to the 23rd molecules of CO2, That means that we have 6.022 times 10 to the 23rd atoms of carbon. However, if we were comparing CO2 to oxygen, we would have twice as many atoms of oxygen. All right, so there's probably some other conversion factors that we could come up with for carbon dioxide and carbon and oxygen, but these are some of the main ones that we can use for solving a numerical problem. So let's use a few of these in an example problem. Let's try to calculate how many moles of oxygen atoms are contained in 11.57 grams of CO2. So first, let's write what we're given. So we're told that we have 11.57 grams of CO2. And then we need to determine how many moles of oxygen atoms we have. And then our plan is a little bit complex because we need to go from grams of CO2, and we need to end up with moles of oxygen. Okay, so going to our conversion factors, we know that we can go from grams to moles using molar mass. So maybe step one, we'll start by converting grams of CO2 to moles of CO2. And then after that, maybe we can use the fact that there are 2 oxygen atoms for every carbon dioxide molecule to get to oh, sorry, got lost in my notes here. So maybe we can use the moles of CO2 to get 2 moles of oxygen using that ratio. Okay, so let's write out this problem and we'll set up our conversion factors, and there's actually going to be 2 steps here. So again, we're always going to start with what we're given. And then our first conversion factor, we want to eliminate grams of CO2. So going back, we said that we have 44.01 grams of CO2 for every 1 mole of CO2. And we do want to get to moles, so let's use that. Okay, so we're going to cancel out grams of CO2, and we want to end up with moles of CO2 in this step. But now we want to get to moles of oxygen. So let's set up another conversion factor. And if we go back to the last slide, we can see that there are 2 moles of oxygen for every 1 mole of CO2. However, we're going to flip that so that we end up with moles of oxygen. So now moles of CO2 will cancel. and we're left with moles of oxygen. So this is going to simplify to 11.57 times 2, and then we're dividing everything by 44.01. And our final unit will be moles of oxygen. Okay, and we should get a value of 0.5258 moles of oxygen. Now, down below, we actually have some carbon dioxide shown. If you've ever used dry ice before, that's actually carbon dioxide. And carbon dioxide is a solid, but it can easily become a gas. So you'll notice that there are some vapors coming off of that dry ice. Okay, and then there's this solution slide if you need it later. So now for the second example here, let's determine how many carbon dioxide molecules are needed to contain 50 grams of carbon. So again, let's start by writing out what we're given. So we're told that we want to end up with 50 grams of carbon in our carbon dioxide sample. And we need to determine the molecules of CO2 required in order to obtain 50 grams of carbon. So our plan here is going to be a little complicated again because we're trying to go from grams of carbon all the way to molecules of CO2. So in step 1, what we probably want to do first is cancel grams of carbon. So one way to do that is to use the molar mass of carbon to go from grams of carbon to moles of carbon. And then once we have moles of carbon, we can go to moles of CO2 just using the ratios between carbon and CO2. And then in our third step, we can finally go from moles of CO2 to molecules of CO2. And we're going to do that using Avogadro's number. Okay, so this is going to be a bit of a longer problem. So let's start with what we were given. Actually, I'm going to use a different color here. And because we have 3 steps, I'm just going to write out 3 conversion factor lines here. So in our first step, we want to use the molar mass of carbon to go from grams of carbon to moles of carbon. So we saw previously that there are 12 grams of carbon for every 1 mole. So that's going to cancel grams of carbon. Now, in the next step, we're going to convert moles of carbon to moles of carbon dioxide, and we need to use the ratio of carbon to carbon dioxide. Now, carbon dioxide only contains one carbon, so that's really easy. We can say, okay, for every 1 mole of carbon dioxide, we have 1 mole of carbon. And then that's going to cancel moles of carbon. And in the last step, we want to convert moles of carbon dioxide to molecules of carbon dioxide. And we're going to use Avogadro's number to do that. So we can put in Avogadro's number, and that is going to be molecules, I'll squeeze it in here, of CO2, and we're going to divide by 1 mole of CO2. Okay, so this is a really long problem, and it might seem a little confusing how I figured out which conversion factors to use, but in a bit we'll go over a flow chart and we'll talk about kind of the path you can follow if you're trying to solve a problem like this. All right, but for now, let's simplify this equation or this calculation. So once we eliminate all of our unneeded units, we'll end up with 50 times Avogadro's number, and then we'll divide that by 12. And I'm leaving out all of the ones because we would just end up with the same answer. And then our final unit will be molecules of CO2. Okay, so if we plug all of this into a calculator, the final answer should be 2.507 times 10 to the 24th molecules of CO2. And we did end up with a pretty large number of molecules, which is what we expect because there are a lot of molecules within a sample. Okay. And then here's a solution slide. In this slide, they used a slightly different approach. So if we go back to all of the equalities we saw for CO2 and carbon and oxygen, we could just simplify a lot of what we did on the last slide. However, in typical factor method problems or dimensional analysis problems, we do go step by step by step, and we use different pieces to kind of get to this point. So whatever works for you, as long as you get the right answer, if you have a different way of solving these problems, that's totally fine. Always show your work so that I know that you know how to solve these problems. But again, my method isn't always the only method. So let's go over a flow chart for some of those more complicated problems. And hopefully this flow chart will help you navigate those more difficult, complex numerical problems. So in problems like the one we just did, it can be a little tricky to figure out which conversion factors to use, or even how to get from point A to point B. So in general, let's say that you're given the mass of an element like we were given in the last problem. You can convert that to moles. And to do that, we would use the molar mass of the element. And then once you have the moles of that element, you could convert that to atoms. Oh, misspelling element here. And to go from moles to atoms, we would use Avogadro's number. Now you can do the same thing for compounds. If you're given the mass of a compound, you can convert that to moles of the compound, and all you need is the molar mass. Now, for a compound, you'll probably have to calculate the molar mass. You can't just look at the periodic table like you can for an element. And again, we can convert from moles of a compound to molecules of a compound. And again, we'll use Avogadro's number. What's great about this flowchart is we can also go in the reverse direction. So if you're starting, let's say, with atoms of an element, you can convert that to moles using Avogadro's number, but you'll have to flip the conversion factor in order to get from atoms to moles. So instead of multiplying by Avogadro's number, you'll divide by Avogadro's number. And then if you're going from moles to mass, you'll still use the molar mass, but you're going to flip it. So, so you're going to multiply by molar mass instead of divide by molar mass. And the same goes for compounds. So I'm going to draw those double arrows there so we can see that you can go in either direction. And then what's also great is we saw in the previous problem that you can convert between moles of an element and moles of a compound. So for instance, we determined how many molecules of CO2 we needed to get a certain amount of carbon. And in order to convert between a compound and an element within that compound, we're just going to use those subscripts or ratios. So for instance, in CO2, we had 1 carbon and 2 oxygens. And then we could also do the same thing with atoms and molecules. We can just use the ratios to determine one or the other. Now, unfortunately, we cannot convert between mass of an element and mass of a compound directly. We have to go through moles first. So masses do not directly correlate with each other, but amounts of elements or amounts of compounds do. And we kind of saw this in the last lecture where even if you have 1 mole of a compound and 1 mole of an element, they're going to have different masses because atoms do have different masses. So another flowchart that you could use if you're trying to go from the mass of an element to the mass of a compound, again, you can't do that directly. So instead, you'll have to go you'll have to convert from the mass of the element to the mass, to the moles of the element. Too many M words. And then we can convert from moles of the element to moles of the compound. And finally, from moles of the compound to the mass. And so I'm really just following the chart up above, but I'm showing it in a different form. So to convert from the mass of the element to moles of the element, you're going to use molar mass. And then to convert from moles of the element to moles of the compound, you'll use any ratios between them. And finally, to convert from moles of the compound to the mass of the compound, you'll use the molar mass of the compound. Okay, so I hope that helps a little bit in terms of solving some of these numerical problems. I also posted a practice worksheet on Canvas, so that should be under modules week 2. And the answer key is also at the end of that document. If you do have any questions on how to solve some of these more difficult problems, please let me know. And I've also posted some extra videos on Canvas under modules week 2 that step through more calculations that are similar to these, but they're videos by Tyler DeWitt and Khan Academy and some other places. So hopefully that helps. And again, you can always email me, or you can also set up a office hour with me through the link on the homepage on Canvas. All right, good luck.